Hi, welcome to Real Learning Center. We are actually starting the fourth video of the series Laws of Motion. So till now you have actually watched three videos, and those three videos actually talk about various things from Newton's first law, second law, and what causes motion, etc. So if you have not watched these videos already, so please go ahead and watch from the beginning, from 1 to 3, and this is the fourth video in the series of laws of motion. So today we are going to cover a new concept called as momentum. Okay, so shall we start? So before actually we start, what we will do is we'll just give a very small review of what we have till now learned in the first three videos, or maybe at least Newton's first law and second law. Okay, so if you look at it, Newton's first law, what we talked about, as said by Newton, is everybody preserves a state of rest or of continuous motion, uniform motion, unless disturbed by an external force. So this is basically what is Newton's first law. What it simply meant was, in my words, lazy law. Okay, where if something is at rest, it will continue to be at rest. If something is in continuous motion with uniform velocity, it will continue to be doing so. Okay, unless an external force acts on it. So once the external force acts on it, things change. So we move from Newton's first law to Newton's second law. Second law is when an external force acts on it, external force exerted on the object, when it happens, the acceleration that is produced is directly proportional to the force and inversely proportional to the mass of the object and in the direction of the force exerted. So again, I'm going to basically split it down into some simpler statements for everybody to understand. Whenever you have external force, it produces acceleration, which simply means when you actually push something, it accelerates. Okay, so that's all it means. And second thing is, whenever the force is more, there is more acceleration, which means when you push more, it accelerates more, means its velocity will increase, speed will increase. And if you actually push less, the speed will reduce slowly if you push. So that is the second part. And the third part simply is, when the mass is higher, the mass increases, acceleration decreases. That means if you have a bigger object, if you try to push a bigger object, it doesn't go that fast. Okay. And finally, the direction of the acceleration is same as the direction of the force. If I push like this, it can't accelerate this way. So these are the four important points of the Newton's second law, which we learned through various examples. Okay, now we are going to now go ahead and understand a new concept called as momentum, and also we will try to understand how the momentum is actually related to Newton's second law. Let's just watch this video on the top first. Okay, so just watch that there's this very small toy car going on somebody, okay, but nothing happens to him. He actually gets up and walks. So what if actually the same thing happens like this with something as heavy as a real jeep, okay, a car, pickup car, so which is falling like that. Okay, it's so heavy and it also has some speed. So if you fall below that, if you get stuck under that, imagine what will happen. So we know very well that if you have more mass and more velocity, you become lethal. Okay, so more mass and more velocity, we need some word for this kind of a product. Okay, so both are actually very interesting. Higher mass and higher velocity, very dangerous. Okay, so we will coin a word which will actually be a product of mass and velocity. Whenever you take the mass, calculate the mass in terms of kgs, and you have velocity in terms of meters per second, and you multiply that. Whatever you get, that is called as actually momentum. Okay, now that is the new word momentum. Whenever you say product of mass and velocity, instead of that you say momentum. Okay, So let us now understand this word, which is actually a product of mass and velocity, okay, with some examples. So here is my first example. So in the first example, you see, I am giving you two options. You have to tell me which one has more moment. Okay, what is the first option? First option is, you can see, I am firing a bullet, and the bullet goes at 200 meters per second, and it is 50 grams. So this is scenario 1. Scenario 2 is, I am just throwing the ball, and the ball goes at 20 meters per second, but it is 500 grams. Now which has more momentum? How do we say this? How do we say which has more momentum, which is more lethal, dangerous? Yeah. So in this case, in this particular case, let's calculate. Okay. The momentum of the bullet is, as we always, we have just coined this word momentum, is basically product of mass and velocity. Mass is 50 grams, velocity is 200 meters per second. So let's multiply. So generally when we multiply, we have this habit of keeping things in one single unit. Okay, it's called SI units. We don't use it in grams, we use it in kgs. So 50 grams means 0.05 kg. Okay, I mean, you could use simply 50 grams into 200 meters per second and multiply and still have the momentum. Just to keep it in the SI units, we can convert it into kgs. It's optional. Okay, 0.05 kgs into 200 meters per second. So if you multiply that, what you got 10 kg meters per second. Okay, kg meter per second is, we have just now figured out, is the unit of momentum, because one of them is kg, other is meter per second. Just club them, kg meters per second. So that is the unit of momentum. Okay, and let us look at the bullet. Now, we have seen the bullet is 10 kg meter per second. What about the ball? So the ball is again 500 grams into 20 meters per second. 500 grams is what? 500 grams is 0.5 kgs. 0.5 into 20 again turns out to be 10 kg meters per second. So both momentums are 10 kg meters per second, hence they are equal. So we can like that say two moments. So don't say these two momentums are equal or not if somebody asks. It cannot be told just by intuitively. You will have to calculate mass into velocity and say the momentums are equal. Now let's take another example. Maybe it will be somewhat clear. Okay, so we have a heavy rock. Okay, basically like 2 tons standing there, and we have a small rat moving at 1 meters per second. So which one has more momentum? So you tend to think that it is rock. Rock has higher mass, true, but it has zero velocity. Mass into zero velocity is zero momentum, because anything multiplied by 0 is 0. Whereas the rat is so small, it is moving at 1 meter per second, it is not 0. So when you multiply it, it is definitely more than 0. In this case, rat wins. Okay, rat has more momentum. So let's look at another scenario. So which gives more pain to your hands? So let's say you catch a ball. Okay, a ball, tennis ball, which is let's say 100 grams, and it is coming at 20 meters per second, and you catch it. Okay, now the same way, let us say I will take another ball which is slightly heavier. Okay, we'll take a leather ball, used in cricket, and which is leather ball is like heavier, but we will make it slower. Okay, so we have a leather ball which is going at 8 meters per second, and it is 200 grams. In this scenario, if you ask which pains more to your hands, so what is your answer? So you can't just intuitively we can't answer this question. So you'll have to calculate what pains more, or you have to catch yourself and see which pains more. One of the two. Okay. So what pains more is whatever has more momentum. See. So the momentum of the tennis ball is 100 into 20, whereas momentum of the leather ball is 200 into 8. So any day 100 into 20, is higher than 200 into 8. So momentum of the tennis ball is more than momentum of the leather ball, and hence we can say In this case, tennis ball hurts more. In this case, okay, tennis ball hurts more in this specific case. It doesn't mean always tennis ball hurts more. I mean, for a specific case, this is the truth when we compare. So now let's move forward and see one more simple scenario. This scenario actually gives you a different outlook of momentum. Okay. So now assume that you are inside, a man actually is inside a train, railway bogie, train is inside, and he is actually carrying a huge luggage. Okay, he's keeping on the chair. You can see it's like 120 kgs of luggage he's carrying. And outside on the railway station, a lady is sitting on a bench. So this is our scenario. Okay. In this scenario, let's say the train starts moving. Okay. So now what will happen? We'll see. So train moving at certain speed, and from the man's point of view, which has more momentum when the train is moving? Okay. The luggage of 120 kgs, which is inside the train, or the bench, which is outside the train of 100 kgs. So just watch it again if you want to. Okay. So the train is moving. Okay. And when it is moving, while it is moving, so the luggage is weighing 120 kgs, and the bench outside is moving 100 kgs. Which one has more momentum? Okay. So it looks inside basically the luggage, the bag is 120 kgs. But what is its velocity? I am asking here one statement. From the man's point of view, its velocity is 0. It is going along with the man. Hence, he will put multiplication of velocity as 0 and get the momentum as 0. Whereas, the bench which is outside, where the lady is sitting, that is 100 kgs. Okay, though smaller than the luggage, but that bench stands still from the outsider's point of view. But from the man's point of view, that bench is actually moving, isn't it? With respect to him, you just look at the bench from your window, you see that bench moves back like this. So the bench is actually moving. So when you multiply that velocity with 100 kgs, definitely there is more than the 0 which you have got for the luggage. So from man's point of view, the bench has more momentum. So however, what about the lady's point of view? That lady is sitting on the bench. What her point of view? From her point of view, okay, the bench is stationary, whereas the luggage is moving. So the bench is lesser momentum, that is 0 when compared to luggage. So the momentum is actually can be different for different people. That means it is relative with respect to their own movements. Okay, the velocity what you calculate is with respect to the velocity from the point of view or from the frame of reference of the observer. That's what we call it. Okay, so it's relative again, momentum. So after knowing this, let's go forward and understand what is meant by change in momentum. Okay, before going to change in momentum, we will also know that momentum is a vector. Okay, it's a very interesting concept. What is meant by a vector? A vector is something which has both a magnitude and a direction. That means you can ask a question, how much, and also in what direction. Two questions you can ask for a momentum. If somebody says that it has some momentum, you can say how much momentum, for which there must be an answer, some number. And somebody may say, what is the direction, for which you should have an answer, saying that this is the direction, some kind of an arrow. Okay. So only when both of them are there, it is called as a vector, and momentum is a vector. Okay. You can see that if the bullet goes this way, okay, and if it goes at a certain speed, like for example, bullet is like 0.1 kg and 200 meters per second, then what is the momentum? 20 kg meter per second. I just multiplied mass and velocity. Okay. Now, if you want to represent it, generally when you say a vector, this is how we write. We write actually one line which is proportional to its value, like 20 kg meters per second. I can write it as 20 centimeters. Okay, so 21 every centimeter actually means 1 kg meter per second. So I can write a line of 20 centimeters, and I will show the arrow mark in the direction of how it went, the velocity. Okay, the moment it went in this direction, so I showed that direction. So this single arrow will tell us about the momentum fully, in direction and its magnitude. And that magnitude means how much. So let's take that ball which is standing there. Let's say if it moves like this, and it moves like this. So this is the direction. So we can draw an arrow, okay, in this direction. Of how much? Find out its momentum. It is 0.2 kgs and it is 50 meter per second. So 10 kg meter per second. So we can draw an arrow which is like 10 centimeters, where 1 centimeter is equal to 1 kg meter per second. That is the scale that I use. So you can draw a line 10 centimeters in the direction of the velocity. So this particular arrow tells us the momentum of the leather ball. Okay. And we also use the letter P to denote momentum. Like for velocity we use V, for mass we use M. For some strange reason, for momentum we don't use M, because M is taken by mass. So for momentum we use P. Okay, so P is momentum. Now, just to have a slight different understanding of what the vector is, if you actually consider, for example, this rock of 100 kgs, yeah, mass is 100 kgs. So how much is the mass? You can ask 100 kgs. In which direction is the mass? Nobody asks that question. So since nobody can ask such a question, mass is not a vector. Okay, no direction, so it's not a vector. It is, we call them as scalar quantities, which are not vectors. So while we are at vector, we will do a little math on vector, okay, and move forward to the momentum back. Okay, so our problem is that whenever you have some new quantity, something called as a vector, we need to understand how to add them, how to subtract them. Otherwise, we have very little we can do with it. Okay, in maths, you know, we already learned from the day one. We learned addition, subtraction for numbers, then for variables, all that. Now we are going to learn it for vectors. How do I add and subtract vectors? Okay. So now, first let's start with addition. Okay, let's say there are two vectors. One vector is one vector is length 4, another vector is length 3. Length 4 vector and length 3 vector, both are in the same direction, you can see. Okay. Now I want to add them. How do I add them? I use a simple principle. Okay, the principle is this. First take the first vector, okay, and write it down. Okay, as is. Put it wherever you want. Then take the second vector and put it in such a way that the beginning of the vector goes to the end of the vector, end of the first vector. That's all. Beginning of the second vector goes to the end of the first vector. So you write that. Now you got actually if you add them both together, you got a lengthy vector like this. And this is like length 7 actually, is nothing but the final added vector. When you added vector 4 and vector 3, you got a vector 7 like this. So what is big deal about it? When you added 4 and 3, we all got 7. So wait and see when it changes. Okay. So now the same rules we go with another vector. Let's say vector subtraction we will do. So I'll see what will happen. So in subtraction, again we have a 4 and we have a 3. How do I subtract? Okay, so what I will do is I will just take the 4 and write it as it is. Okay. Now I will take the 3. Since I have to subtract, I have to actually reverse its direction and write. Okay. While writing, again, I will make sure that the beginning of my second vector rests on the end of the first vector. Okay, that is what I will do. I will take it, turn it around, put it like this. The beginning goes to the end. Now finally what I will have to do is that to find out the final, you start from the beginning of the first vector until the end of the second vector, I draw a line. Beginning of the first vector till the end of the second vector, I drew a line. That is just one now. So this is basically the subtracted vector. When you subtract it, it is how it looks like. So this again is quite intuitive because 4 minus 3 is 1. Nothing great about it. Okay. And let us see another scenario where it starts to become important, our ideas. Okay. Let's say I have two vectors like this. They are not in the same direction. They are in some upwardly different directions. So there is a 4 and there is a 3. Now, what do I do with it? I have to add them. How do I add? So I will again use basically a similar technique, but this time I will actually invent a slightly newer technique. Okay, there are two techniques. So just now I told you one technique. Now I am telling you another technique. In this technique, what I will do is I will take the second vector. First vector I will keep it as it is. Second vector I will take, and beginning of the second vector I will put at the beginning of the first vector. See whether it is possible. Okay, take it. See, it is very different from what till now I used. This is a different technique. So this is called a parallelogram technique. I took the second vector, beginning of the second vector, and put it at the beginning of the first vector. So after that, these two lines I will take and I will complete a parallelogram. So I will just draw these two lines and make a parallelogram. So once you make a parallelogram like this, okay, now I will draw the diagonal like this. Okay, and that diagonal represents my added vector. Okay, 4 and 3, if I add, I get that vector, and definitely it is not 7. Okay, it is some other number. How do I know? You draw and see. You draw 4, you draw 3, draw a parallelogram and just measure it using your scale, and you will see that it is a different number. So, vector addition is very strange. Okay, you need a parallelogram for that. What about vector subtraction in this scenario? We can do a subtraction also. Let's say I have a 4 and a 3 like this. I want to subtract. For subtract, I will have to reverse 3. Okay, 3 is basically minus 3 now. So I will have to invert the direction of the 3. So what do? I actually take 3 and turn it around and put it like this. Once I put it, becomes minus 3. So what I will do? I will now complete the parallelogram of that one. I complete the parallelogram. After completing the parallelogram, wherever the starting point of both the vectors, from there I draw a diagonal. From the starting point of both the vectors, from there I draw a diagonal. And that, the yellow one basically, is the final vector, subtracted vector. Okay, so that is another way of subtracting. So just learn this technique of subtraction and addition, because we need it when we want to add and subtract momentum, or even when we want to do add and subtract forces, we need these techniques. Okay, so the next thing that we want to do is try to understand change in momentum. We'll get back to momentum now. We understood now how to add and subtract vectors, and momentum is a vector, so we will use it. So what is meant by change in momentum? So let us say a car is moving, okay, and it sees a road which is not so good, and you brake. Okay, so now what happened to the momentum? So you see, initial momentum is 1000 kg into 40 meters per second, which is like 40,000 kg meters per second. Final momentum, that means after you slowed down, the final momentum is 1000 kg into 10 meters per second. It is just 1000 kilograms meters per second. So I just want to see it again. So look at this basically. You start from here, and you whenever the road becomes bad, you start braking. So you can see how it slows down. So when it slows down, since the velocity changed, the momentum also changed. Before it slows down, we call it as initial momentum. After it slows down, we call it as final momentum. So change in momentum is simply nothing but final momentum minus initial momentum. Okay. So we will represent the initial momentum in an arrow. Like 40,000 kg meter per second is an arrow. Okay. And 10,000 kg meter per second is another arrow, which is of course 1/4 of the length of this arrow, because it is only 10,000. Now, directions are same though. Okay. So I want to find out the change in momentum. That is nothing but final momentum minus initial momentum. So how do I calculate? So what I will do is I will take the final momentum, that is the first one, and keep it here. Okay, first one I will do the vector subtraction. So for that first one I will take and keep it here. Okay, now second one when we take, because it is minus, I need to actually do the reverse, okay, because it is minus. So first one minus the second one. Okay. So I will reverse it and keep it in such a way that the beginning of this vector, the longer vector, starts at the end of the second vector. So I will just take it and keep it like this. After keeping it like this, now I am going to draw from the beginning of the first vector till the end of the second vector a line, and that is the line, and that line is representing change in momentum. So this is a vector representing change in momentum. So this is called a change in momentum vector. Okay. So this yellow vector. So we got a vector which is change in momentum vector. Now it is also called by another name called impulse. Change in momentum is called by a name called impulse. Okay. So we can say that this is the impulse vector. Now let us see the impulse vector in another scenario. Let's take a carom board and let's calculate the change in momentum of the striker. Okay, the striker starts from here, and let's say you hit it to the opposite boundary, and it hits and comes back. Okay, now when it hits and comes back, so let us just plot initial momentum before hitting and final momentum after hitting. Initial momentum before hitting is like this, in this direction. I will call it as, since momentum is P, I will call it as P initial. So after hitting it will come back. No? That is called as P final. Okay. So P initial, P final. They may be almost equal many times. Okay. P final may be slightly less than P initial. So that magnitude depends on its velocity after hitting. So you got P final and P initial. Now we have to find out what is the change in momentum vector looking like. This is just a practice to find out how to draw a change in momentum vector. So in this case, what we will do, we will just take the first vector and keep it as it is. Okay. So now we will call this change in momentum as delta P. Okay. The word delta P is for a triangle P. You see there is a triangle here. So the triangle, when you write, it means that when you two values difference when you take, so we will actually represent it as delta P. That means some triangle and then P. It's the difference between the two. That's all. Nothing big about it. It is one notation. So P final minus P initial is basically what we write here. Okay. So how do I calculate that? P final. First I will take and keep it here. Okay. I got the P final and kept it here. So I got it. Now when I am taking P initial and keeping it, I will keep it at the end of the first vector, and I will also turn it around because it is negative. So I will take the second one and turn it around and keep it. So now I will start with the first vector, the beginning, and end with the second vector's end and draw a line. And that is my delta P. So we found out change in momentum vector. So this is one technique to find a changing momentum vector. Now change in momentum vector can be also calculated in slightly more complex scenarios. Let us take this scenario. So here again we will do that. So there is a tennis bat here and a tennis ball, and ball takes this kind of a path. Okay, it hits and goes like this. Now let us look at what is the initial momentum and change in final momentum, and how much momentum is changed by hitting the bat. Okay, so initial momentum vector again is, we call it as P initial in this direction, and P final is in this direction, final momentum vector. Now what do? We actually take the initial moment. So we have to find out, what do we have to find out? We have to find out P initial, P final minus P initial. So P final we keep it as it is. P initial reverse the direction. Okay. So how do we do that? We can reverse the direction like this. Okay. That is becoming minus P initial. So now I want to find the resultant, so I create a parallelogram using those two, and I draw a line from the beginning of the both till the, so this arrow, yellow arrow, is called as delta P, or change in momentum. So in three different scenarios we figured out how to find the change in momentum. So once we now master this art of finding out the change in momentum vector, now we will go one step forward, and then we say that we are going to introduce one more word. I promise you last word. Okay, it's called rate of change in momentum. So what is meant by rate of change in momentum? Now you watch both these cars, both the cars. Okay, both of them will actually start at the same time, and both of them will acquire the same velocity. But there is a difference. Tell me what is the difference. Okay, just watch it. Okay, I'll again show it to you once again. If you want once again, I will show it to you. Okay, just watch it now very carefully. Both of them actually acquired exactly same velocity. However, the first one, the top one, basically acquired it pretty quickly. The second one acquired a little slowly. Okay, so what it means is basically both cars had exactly same weight, exactly same mass. If you saw them, they looked exactly similar. And both cars were initial velocity 0. They were standing. Both of them were standing. Initial velocity is 0. So 0 into mass, momentum is 0. Initial momentum is 0. Both cars actually acquired a final velocity of 5 meters per second. Okay, so final momentum is 5000 kg meters per second. So 5 into 1000. Okay, so that is also known. Both cars is same. So what is the difference? For both cars, change in momentum is same only. Delta P is nothing but 5000 minus 0. Final momentum minus initial momentum. That is 5000. So delta P is same for both of them. But what is different is first car achieved this change in less time. Hence, the first car has higher rate of change in momentum. Higher rate means increases fast. It's called higher rate. So since it did it in very small time, it has higher rate of change in momentum. So in order to have higher rate of change in momentum, the engine has to actually apply higher force. So the first car needed more force to change the momentum faster. When you want to change the momentum faster, you need higher force. And that brings us back to Newton's second. So Newton's second law has another statement, okay, which is equivalent to the first one. Okay. Force applied here is equal to rate of change in momentum. So we said that if you want to have a higher rate of change in momentum, that means if you want to quickly change its momentum very fast, then you need to apply more force. This is another way of stating Newton's second law. So Newton's second law has a second definition. So you can read this here. If an external force is applied on a body, then the rate of change in momentum will be equal to the force applied and will be in the direction of the force. Rate of change in momentum, we calculated, not change in momentum vector. Force will be in that direction always. So that is the Newton's second law. So this is alternate form of Newton's second law. Force applied is equal to rate of change in momentum. Remember that. So now I will just give you a very simple real world example of this. Okay, just keep watching this. So here actually what happens is a ball is thrown from the top and a player catches the ball, and just keep watching how he catches the ball. Okay, watch his hand movement very carefully. Did you watch his hand movement very carefully? Once again. Okay, so what actually happened was he does lower his hand while he is catching the ball. You can see, just like this. He lowers his hand. He just doesn't hold it like this. He does like. Why does he lower his hand? It has some connection to Newton's second law. Tell me, why does he lower his hand? Okay, the answer is, see, look at this. The ball, okay, since he needs to stop the ball, he has to stop the ball to be able to hold it. So that means that it has certain momentum, and when it comes to his hand, the momentum should become 0. Okay, now if he keeps it in his hand directly like this, it comes and hits his hand. That means it has to become some momentum. It's already, its mass into velocity to become zero. It's a huge change. So that huge change, if you want to bring it in small amount of time, yeah, you're just holding it here. If we go a little less, this much, in this much amount of time, you have to make it zero. That means for that your hand has to apply a lot of braking force to the ball. Whereas if you do it like this, your hand will slowly change the momentum, and hand has to apply very less force for that. Okay. So lowering the hand basically increases the time duration for which you are actually bringing down the momentum. Rate of change of momentum is less. Change in momentum is same. It has to become zero. But rate of change of momentum is less. You are slowly bringing down. So that means rate of change of momentum is same as, according to Newton's second law, the force. So you are reducing the force which you have to basically act on the ball. You have to break the ball, the force that acts on the ball, so that the ball is slow. Why do you do that? Two reasons. One, if you just hold it like this, it might hit your hand and then bounce off. Okay. Or secondly, it might hit in hand. You may hold it also, but it is going to hurt your hand because the force it requires to stop is very high, and that force is given by your hand. Your whole muscles will inside hurt, and you might even break some bone if you don't catch it properly. But whereas if you do it like that, then you are slowly doing it, and hence the force required is less. So that is a real world view of Newton's second law. Okay. So what have we learned till now? We have finished what causes motion, Newton's first law, Newton's second law, and we also understood now a momentum, which is basically a mass and velocity product, and how is that related to Newton's second law, that we have figured out. So please come back and visit more videos, and here we have 2 more videos to finish, Newton's third law and finally the collision. So till then, thank you, good night.